Beginning of analog electronics videos 30 through 39, which center on the voltage controlled oscillator, or VCO. Today is an introductory lecture. I'll be talking about what is a VCO, and then showing a simple 555 timer oscillator design, which gives some output waveforms which are voltage controllable, but not particularly sharp. I'll talk about a recent solution that's come up in the DIY literature for creating nice looking sawtooth waveforms, which are ideal for a lot of subtractive synthesis due to their high harmonic content, by using a transistor on the charging arm of a 555 timer. And then I'll demonstrate it with external voltage control, and a particular device that has some simple tuning. I will be building actually the device I designed. I think for a student it's an interesting thing to do, but not necessary to build my design here in Analog30. I will demonstrate how to tune a VCO, or at least maybe not give a procedure, but show what the process is like, using our manual sequencer, our push button sequencer, which produced three different control voltages, 0, 1, and 2 volts, that we designed, characterized, and tested, and then buffered the output of in lectures 26 through 29 previously. Starting with Analog32, we jump into the actual construction of the Thomas Henry 555 VCO, which is a very nice oscillator and is the one included in the course kits. We'll be testing that with a oscilloscope in Analog38. In 39, then we'll talk about some more theory on advanced VCOs, and by then you should have an appreciation for what they do and actually be making some pretty good sounding notes. Look ahead is at the next series of lectures, 40 through 49. We'll be on designing an 8-bit sequencer module, included printed circuit board design. This takes our manual sequencer that produced 0, 1, and 2 volts, and instead uses another 555 timer, as it turns out, to create a whole sequence of notes which you can dial in a separate module. So that's what's ahead. So what is a VCO? I've just put up the Wikipedia definition here. Now keep in mind I've assigned reading from Make Analog Synthesizers on VCOs, but just to review, a VCO is an electronic oscillator whose oscillation frequency is controlled by a voltage input. As the voltage changes, the instantaneous oscillation coming out changes. It can be used then for frequency modulation effects, where if you change the voltage slightly coming in, you will get a modulated frequency going out. They're also used in many other electronic devices. Some of them are listed here. Phase lock loops, which allow multiplication to higher frequencies in a synchronized fashion, or a very useful device in a physics lab, which is a voltage to frequency converter, which allows you to transmit information about voltages over long ranges, since frequencies often are easier to reproduce with high accuracy than voltages over distances through transmission lines. So it's a very generally useful thing, and VCOs are found all the time in electronics laboratory as benchtop function generators, frequency synthesizers, and as it mentions here, and of course the production of electronic music to generate variable tones in synthesizers, and that's more our primary purpose here today. Notes that function generators usually feature multiple waveforms, typically sine, square, and triangle waves, among others, and we'll be working on generating some of these different sorts of patterns in our VCOs. Audio frequency VCOs are used in analog music synthesizers. For these, sweep range, linearity, and distortion are often the most important specifications. And of course, in some senses, as Wikipedia implies, audio VCOs are somewhat of a dinosaur, been largely supplanted, of course, by digital counterpart parts, and now even more likely simply generating notes in software. However, the resurgence of interest in analog electronics for music, particularly modular analog synthesis, has driven a lot of renewed interest in VCOs. So I want to say a word before we get started about VCO tuning. I've talked about that quite a lot and we'll keep coming back to it. The standard that's used in many, but not all, modular analog synthesizers going back many decades is 1 volt per octave. That is to say that if you, for instance, were to set 2 volts to mean 440 hertz, 3 volts would be 880 hertz, and 1.0 volts would be 220 hertz. So you go up or down by an octave by changing the voltage by 1 volt. Now, that choice of, say, 440 hertz being 1 volt is absolutely at the discretion of the user, and typically you might want to tune or even purposefully detune several different VCOs. VCOs, if they're good, can cover a huge range, 8 or more octaves. So you're talking pretty much the whole range of human hearing, and the one that we'll be building certainly appears to have that range. Challenges come from this large tuning range primarily. It's hard to maintain 1 volt per octave, so you might have a problem where you are at 1.1 or 1.2 volts per octave at the lower range, but 0.9 or 0.8 volts per octave at a higher range, for instance. This can lead to a problem where you're not able to accurately reproduce the music you want to make because you fall out of tune as you go up or down the scale. Another challenge is tuning multiple VCOs or tuning them to an external standard, like, say, a tuning fork, can be tricky to get them there. And then also, number 3, to hold them there, especially as temperature drifts. Because we have an exponential scale where the frequency is doubling every volt, it's particularly hard to maintain low temperature drift. And it comes from the nature of using transistors to accomplish exponential conversion. We'll talk a bit about how that can be done and regulated. Finally, number 4 is a big difficulty is crisp waveforms. I'll give you a quick introduction to how that works here in just a couple minutes. Again, the design that we'll be doing starting in a couple lectures, designed by Thomas Henry. His 555 VCO does an excellent job of meeting most of these challenges, especially in a inexpensive and relatively easy to build device that uses common parts. We'll be building a simplified version of that classic design. If you want to look at the Wikipedia article on voltage controlled oscillators, I encourage you to do that. And also definitely please read that section in Make Analog Synthesizers on VCOs. This is a diagram for a full VCO, and I'm going to point out the parts in the Thomas Henry design later in this series of videos we'll be building. We will have an exponential control voltage in, so that's 1 dB per octave. We'll have just one line of control voltage in. We will not have any linear modulation in, but we will have adjustments for coarse and fine frequency tuning. We'll only have 2 waveform outputs. We'll be making a triangle or ramp waveform and a ramp waveform or sawtooth waveform, and then a triangular waveform, which is not a bad approximation to a sine wave. We will not be designing right away, although they make for great final projects. VCOs or converters which give you opposite polarity ramps, modulatable square pulse widths, or true sine waves, nor will we have the ability to sync it externally or adjust the pulse width that comes out. Okay, so here's a Lush Projects simulation of a VCO, which is not voltage controlled yet, so just an oscillator, I should say, based on the familiar 555 timer or something very similar to what we built last quarter. I've used a pot with a loopback configuration, so I have a variable resistance that allow me to change the charging time of this 10 nanofarad capacitor. The output is taken just above the capacitor right here. So you can see the not trigger and threshold are set to the same voltage level. So it's really just a question of how long it takes this capacitor to charge and discharge that determines how quickly the oscillator flips. So it's a very simple sort of oscillator. Other connections are, of course, ground. Reset is held high, so the oscillator is always running, and voltage in is simply connected to a rail voltage. And right at the moment, I'm just showing it running off a 9-volt battery. Slide this over here and look at the waveform for a moment. We'll see as I change the resistance in this case, the capacitor charging time will change a little bit. And you can see the frequency has gone up, as in this case I've made that resistance smaller. Back. I'm going to stop the simulation at the moment and let's look at this waveform. We know we're dealing with the process of charging and uncharging a capacitor, and from the supply, I presume the battery is always providing a constant voltage, and so we know with constant voltage charging of a capacitor, we have this exponential curve that represents how long it takes the capacitor to charge, and it gets to the trigger point on the 555 timer, and that's when it discharges quickly and then starts charging again. This shape is not ideal. We would like to have a nice ramp where it was a straight line rather than a curved line. And so I started looking around and found that there was quite a clever idea that appeared in the online magazine Hackaday, highlighting this different design, which put a transistor to regulate current in a similar 555 oscillator, still taking the output right over this charging capacitor. Looking at the actual article, I grabbed the details off it, and the author, Tristan, had an interesting admission. He said he built this sawtooth oscillator out of a 555. It can be done contrary to what I said in a previous post, and sure enough, this same author had said, well, I never want to use a 555 timer as an oscillator in a musical oscillator because I can't get nice sawtooth waveforms. And so he came up with this trick, which was to supply regulated current to the timing capacitor, which creates a linear ramp. In other words, he's going to charge this 10 nanofarad capacitor not at a constant voltage, but with a constant current, because as you recall, transistors, at least count PNP and NPN transistors as a PNP shown, give you a constant current regardless of the voltage change based on the current that goes into the resistor. And you can see his configuration is a constant current in the resistor. Here's a simple voltage divider determining to what extent that the transistor switch is open or not, right? Because the transistor is controlled by the base. The base current controls for a PNP what flows from the emitter to the collector, and therefore that current rate is carefully controlled by the transistor and this ratio of resistances. And then it's just a matter of throttling, in his case, the amount of time it takes for this capacitor charge or discharge by changing the resistance here. So I built this one up in a simulation also, and all the links for these simulations are in the comments of the video as well as in the course notes. So I've just duplicated what he had, put a pot I kept up here for controlling the discharging rate, but then I made this a constant current supply rather than a constant voltage supply by switching over to his design. And we can see, I'll stop the simulation here. Still, again, voltage control works, but look how nice and straight that line is. And what this means is that the Fourier components are going to be particularly wide-ranging. These really nice, sharp kinks that you get top, this crisp waveform. Those spikes are going to end up giving you lots and lots of harmonics, which you'll be able to play with later to tweak the sound to get what you want to hear. Again, it would be tuned with this resistor though. It's not yet a voltage controlled oscillator. To do that, one more set of modifications. I put a fixed resistor in here and replaced this constant voltage divider with one that I could tune externally. And so here's my diagram for that. All right. We can see I still have the nice sharp waveforms down here, so I'm happy. But what I've added is all this stuff over here, which is basically determining how much current goes into this transistor. Now, just a word right now about transistors. We recall that they have a exponential gain. That is, if you put a little bit of current in, you get an exponentially larger amount through the transistor. And that is exactly what we're taking advantage of to do the conversion from volts to octaves, because we have to, again, double for every increase in octave. But how do we get exactly a doubling? Well, first of all, I bumped our rails up to this standard for our Eurorack plus 12 and minus 12. I still do have a ground available where needed. And then I put a potentiometer in to control the amount of current going to the base. So this is just the voltage divider from last time, where I can control the amount that goes in by bringing in voltage externally. So this 2 volts is controlled externally. And what you see here is basically a small gain, fixed gain amplifier working as a follower, and getting the polarity right. So here, as I increase the voltage, shown here from, or I should decrease the voltage, currently at 2 volts, I'm at 134 hertz. So it is, if I were to stop the simulation and count the amount of time, I would see that 1 over this period would be 134 hertz. And now I'm going to drop the voltage by 1 volt. I've gone to 72 hertz. Well, 72 times 2 is actually 140 hertz, so I'm almost but not quite at an octave of tuning. And by changing this pot, I would be able to change the center frequency, and this one, that range of getting around a volt per octave. The problem is I can't really change, and you can find this by experimentation, the voltage that I get out of the input. So this is our volt per octave input, without having to retweak a little bit the range potentiometer up here. But this is a neat idea. It was enough for me to say I'm going to try to understand what's going on and build it. And one of the reasons I've shown you this process I went through is so that you understand what you have to do on your final projects when you start to design your own module. Find something interesting in the literature, try to understand it, try to stimulate it, adapt it to your particular needs. Okay. Here's what I built. I did end up going and soldering it together on a nice piece of proto board. Maybe we'll recognize the Geek Fun proto boards, which resemble a breadboard, but just with places to solder components. To identify a few things, here's the first pot. That controls the output out of the op amp. Here's the second pot. Second pot, which controls the tuning range. And this upper chip, if you look closely, is the TLO81 op amp. So this is the op amp here at the entrance. And this chip here is a 555 timer. And looking at the 555 timer briefly, you can see it's hooked up to power. It's hooked up to ground, and the input is coming into it via this transistor, whose base is ultimately controlled by these pots. So there's the transistor, there's the 555, there is the 10 nanofarad capacitor, and then the output is here on the orange pin. Now, not shown on my diagram is existence of another follower, which is exactly like the input op amp. I just put an output op amp, but with a simple feedback, as we did at the output of the sequencer circuit. This insists that I be able to drive any load with this output. Gives me basically a zero Thevenin resistance output for my VCO. Okay, the input then I put on a 3.5 millimeter mono jack, and the output on another 3.5 millimeter mono jack. So this is the voltage in, and this jack is the oscillations out. And on the back side I soldered, you can see on the front here, I soldered a 10-pin IDC connector, so I could just bolt it onto the front of my Euro rack for testing. I haven't made a nice plate for it because it just doesn't give such great results, but we're going to listen in anyway. That was the design and the construction. Let's play it. There you go. All right, so I have action of the two different tuning pots, one for setting the tuning, one for roughly setting the range, and we could hear the output going through this jack to a speaker. Notice I was not bringing in any external voltage in this video, and that'll be true of the VCOs you build as well. They will play without an external input voltage because the input is simply grounded the way these are built if there is no plug going in the jack. So it's playing the 0 volt note, and I was setting what 0 volts meant by using this potentiometer here. One more time. Notice the clicking when it's below audio frequencies. As it moves up to high range, we lose entirely our ability to hear it. And it's got that very, very biting sawtooth sound, which, although it doesn't sound great on its own, is again ideal for subtractive synthesis. In the next video, we will look at putting something into the input, in particular from our buffered manual push button sequencer that we built in videos 28 and 29.